yeah, this number is what it is. It's a table value. But we would have a bigger number down there rather than 1 atmosphere. Maybe it would be 2 or 3 or however big we wanted to make the pressure. That makes the denominator bigger, which makes this number smaller. So we're subtracting a smaller number. And actually, you could make it so that this number is less than 1. And the log of a number less than 1 gives a negative number. So you're subtracting a negative number, your cell potential would be higher than 0.34. You see that? So yeah, using the math on this, if your Q value is negative, no, if your Q value, this term in the parentheses, is less than 1, 10 to a negative power, that makes the log of it negative. Yep. Got a hairy pencil. All right, anything else about this example? Now, I have another example that we're not going to do. I'll show it to you, and hopefully you'll be glad that we're not doing it. Yeah. Oh, thanks, Mark. Did you move it so that you could put it? Oh, thank you for doing that. I didn't know if that would still be on there. Thanks. All right, so yeah, I'm not going to take the class time to do this because we need to at least start electrolysis. But yeah, now, the reason that we would need the KSP value is because we have a copper electrode. And you know how last time it gave us what the initial concentration of copper was? It told us copper was 2.5 times 10 to the negative fourth. In this example, it doesn't tell us what the initial concentration of copper is, but we have to figure it out from the KSP value. Those doomed dolls. Let's do something else.
So extra.
This is a very simple thing. I think there's one book exercise that has a relationship between the cell potential and the equilibrium constant. Now, we've seen a relationship between delta G and the equilibrium constant. That's delta G equals negative RT ln of K. Let's just check out what happens here. This is just like I say, it's very simple. If you have a reaction that's at equilibrium, we know what equilibrium means. That means this rate is just as fast as that rate, so nothing's happening overall. So if that rate is equal to that rate, then the reaction's not going anywhere. It's like at a stalemate, and the voltage would be 0 at equilibrium. That's the only time you can have a voltage of 0, is if the reaction's at equilibrium. If it's not going to the right and not going to the left. So we could just use the Nernst equation, and we could plug in 0 for the cell potential, because that's what it is at equilibrium. And that ratio of products to reactants, if it's at equilibrium, we'd call it K now, not Q. So just rearranging this thing, taking this whole subtracted term and moving it over and solving for log of K, we have this. And that's really all that's on the screen for this slide. Is the log of K is equal to, you just move the N over, multiply it by the cell potential standard, divided by 0.0591. This relates the K to the cell potential. So the bigger and more positive the cell potential, we know that would be spontaneous, and you'd have a big K value, which means it takes a long time to make a lot of products before you get to equilibrium. If the cell potential is very small, then you're going to have a very small value of K. That means that it's not going to make much product. So you may need that. That would be a simple derivation if you had a test and you didn't really know this. I think you could figure it out, just understanding that at equilibrium there's no voltage, so that term is 0. Then just solve for K. I don't even have an example. It's just very simple plug-in kind of work to do with that. So I'll just leave that one to you when you run into some. This is the last thing that we'll talk about today. I'm going to have this slide and then one other slide and we'll quit. Would the drinking bird help? I mean, does that maybe add some stimulation?
I think so.
What? I think so. I haven't heard anything about it. Unless it's flown away. This is nothing new. This is what we've been doing. We call this a galvanic cell. Also known as, what's another name for a galvanic cell? Electrochemical cell. There's one more name for it. Starts with a V. A voltaic cell. Right. That was all in the reading assignment that you did last week. Yep. Galvanic cell, electrochemical cell, voltaic cell. All of those will take a spontaneous reaction, separate it into compartments, and there will be a flow of electrons from the anode to the cathode. It happens spontaneously. That's what a galvanic/voltaic cell is.
Are you always supposed to draw the anode?
You don't have to, but I always do, just to be consistent. I was trying to keep my hydrogen close to this board for the sake of people who are watching the vlog. You see this word up here, electrolysis? Some of you have biology. The root here, L-Y-S, means what? Lyse. To break apart. Yes. We'll go with the breaking apart. So we have breaking apart. Lysis means breaking apart. And electro means, of course, the flow of electrons. This is not a picture of electrolysis. This is a picture of a galvanic cell. Electrolysis is something different. I just wanted to remind you, this is what we've been doing. In contrast, here's what we could do when we use electrolysis. Electrolysis is the process of using an external current to push the electrons on purpose in the non-spontaneous direction. We're going to force the non-spontaneous direction. Electrolysis.
The cell.
Electrolytic cell. Now, down here below the shade, I'll pull that off in a second. It's going to look like this, but usually with electrolysis, we'll just have 2 electrodes in one beaker. You could have a 2-beaker system, but for electrolysis, normally we just use one. And after today, I'll show you what that looks like. Oh, no, I guess on the next slide we'll see that. This would be an electrolytic cell. Okay. Notice this time in the electrolytic cell, we have an external power supply that's built into the system. This power supply needs to be plugged in to the wall, and it's going to force electrons to come out of this thing, this side, out of the copper side, and go into the zinc side. Now, spontaneously, they should leave the zinc, the electrons should leave the zinc and go into the copper. But this power supply is going to force the electrons to go the other way. I brought a power supply with me just so you could see it. We'll talk about it in the next slide. So you could wind up with the same reaction, but reversed. You could reverse the reaction by force. And it will not happen spontaneously. That's why you need that plug-in power source. No, because look at the direction of the electrons flowing. This is the spontaneous direction, where this is losing electrons, that's gaining. That would have a positive cell potential. This, the spontaneous direction is still that way, but that power supply is forcing the electrons to go the other way. So because the electrons are leaving here, that has to be the anode. Something has to be oxidizing over here, and something has to be reducing here. Yeah?
Is 1.1 the amount of pulse you need to reverse the reaction?
Yeah, if the reaction goes spontaneously at positive 1.1 volts, then you need to take your power supply and turn the dial up to greater than 1.1 to force them to go. If you go to exactly 1.1, the thing's at equilibrium. The electrons are trying to go that way naturally, but your power supply is trying to force the electrons that way. And so both sides are pushing at 1.1 volts, nothing would happen. So that's why I say it's got to be greater than 1.1 to ultimately get the electrons to go over there, from right to left. Now the simplest electrolytic kind of cell is where you electrolyze a salt. Like you just take a simple salt, and the best example I can give you is sodium chloride. Good old salt, sodium chloride. That's what the next slide has. Next slide has the electrolysis. Now, when you have a solid salt, the particles are in the solid phase, and they can't migrate. They can't move around as a solid. So in order to get this to happen, you need to have the salt melted down. You have to have liquid salt. Which is not terrible. You could heat up sodium chloride and make it go down to a liquid. Yep. That phlogiston demo that I did the other day with the candy cane in there, that was spewing liquid sodium chloride and splatters all over the countertop.
Wait, what candy
I was doing it in my Chem 1 class where we have fun.
cane? I didn't have fun.
I did.
It'll be fun after May.
Mm-hmm.
There's only like 10 days after me.
This is a long time. You'll get bored.
It's like a month.
Yeah.
Will we be taking our final after we
Senior?
do the AP test?
No, you'll take it the Friday before. The AP exam is on a Monday, so that Friday before the AP exam, we'll have our class final exam.
Oh, so does that mean like during finals week we won't actually have a final on this?
Right, we'll have a lab. We'll do a lab on our finals day.
We'll be like
Yep.
working.
Yep.
We would go-
And JD, you need to come back.
Yeah, gotta visit.
Okay, so anyway, this is a spontaneous reaction the way that it's written. If you look at the arrow, and if we were to find the cell potential for this reaction, it would be a very positive number. Sodium chloride is much more stable as this than it is as those two things. So sodium is very willing to oxidize to Na+. Chlorine is willing to reduce to Cl-. So this is a definitely spontaneous reaction in the forward direction. If we electrolyze this thing, we would take sodium chloride and we would split it into sodium and chlorine. That is not spontaneous. If it's spontaneous for these two elements to make the salt, then that means it's not spontaneous for the salt to turn back and make its elements. That's what this says right here. So we could do it. We could use an external power supply, and again, the salt has to be liquid, so you've got to heat it up really, really hot so that the ions can kind of flow around and the charge can move. And the cell would look like this. This would be the electrolytic cell in molten sodium chloride. So notice the sodium chloride is the liquid. There's only one beaker. We got melted sodium chloride in one beaker, and you put the two electrodes in there. And then the two electrodes are connected to this power supply. Yes?
Melting point of sodium chloride is 800 Celsius.
It's about 800, yeah. Did you just look that up? Nice. So we can do that. I mean, that's not outside of the realm of possibility. We can melt down sodium chloride.
Or, for the perspective of 1,734
1700 degrees Fahrenheit. Yep. Our burners, the Bunsen burners, get to about 600 or 700 degrees Celsius. And then we've got some of those big boy burners, the Fisher burners. They'll go higher than that.
You need a forge.
No, you just need like 2 burners.
That doesn't work like that.
Sounds good. All right. So now here's the key for this power supply. So we have just liquid salt down there. Now the liquid salt, just because you make it a liquid, doesn't mean that it's going to split apart. It's still very stable as liquid salt. And you're not getting any sodium, the metal, or chlorine, the metal, until you put the 2 electrodes in there. They're made of platinum. And you connect those 2 with the wire into a power supply.